Good morning, everyone. Myself Shomojit Nayak from third year EC department. In this video, I am going to explain my digital communication laboratory experiment number 4, which is uniform quantization and pulse code modulation or PCM. For this experiment, I have used Python in Google Colab, mainly with NumPy and Matplotlib to perform complete simulation. So let's start with the basic concept. So we have to know what is quantization. Basically, quantization is one of the important steps when we convert an analog signal into digital form. An analog signal can have a continuous range of amplitude values, but in a digital system, we cannot represent every possible value separately. So what we do is divide the complete amplitude range into a fixed number of levels. Then each sample of original signal is assigned to nearest available level. Because of this approximation, the quantization signal is not exactly the same as the original signal. The difference between the is called quantization error. Okay. Uh, Now in this experiment, we are using uniform quantizer. Uniform means that distance between two consecutive quantization level is same throughout the entire input range. If we use n bits, then the number of level is n equal to 2 to the power n. For example, with 3 bits we get 8 levels. With 8 bits we get 2 to the 256 level. The step size, which we call delta, is the total input range divided by the number of levels. Okay. Now let's talk about the error. The quantization error can simply be written as equal to x minus xq, where x is the original sample and xq is the quantized sample. The important thing to understand is that if we increase the number of bits, the step size becomes smaller. So the quantized signal becomes closer to the original signal. The quantization noise power is approximated delta square divided by 12. Okay, here you can see. Because of this relationship, adding one extra bit improves the SQNR, signal quantization noise ratio, by approximately 6.02 decibel. SQNR means signal to quantization ratio. It basically tells about how much stronger the useful signal is compared to the quantization noise. For a full scale sine wave, the theoretical SQNR is given by SQNR equal to 6.02 n plus 1.76 decibel. So this formula is something we will compare with our practical simulation result. Now coming to the point, PCM or pulse code modulation. So we have to know pulse code modulation. Pulse code modulation or PCM is mainly involves three steps. First is sampling, second is quantization, and third is encoding. So first we take samples of the analog signal. Then each sample is converted to one of the available quantization level. Finally, we corresponding level is represented using a binary code. That binary sequence is PCM output. Okay. Now see, the I have actually done in Python code. Here you can see I generated 5 hertz sinusoidal signal. Okay, here you can see 5 hertz sinusoidal signal with amplitude 1. I used 10,000 samples for 1 second, and in the input range was taken from -1 to +1. And then I created a function called PCM quantizer. Inside this function, here you can see this PCM quantizer. Here you can see PCM quantizer. Okay, and inside this function, first the number of level is calculated using 2 to the power of bits. Okay, then the program calculated the step size, and after that, for every sample, it finds the appropriate quantization index. The index also restricted it between 0 and L units. 0 and L 0 and L units. Okay. uh, 0 and sorry 0 and L minus 1, that it stay with the valid range. Then the quantization value is calculated. Finally, the index is converted into a binary code word with the required number of bits. And after this, I tested a quantization for different values from 2 bits up to 8 bits. Here you can see point number 3. And for every case, the program calculates the MSE or mean squared error and the measured SQNR. It also calculates the theoretical SQNR using the formula we have already discussed earlier. And now we go to the result. And here you can see the result. Um, and now you see that at 2 bits we have only 4 levels. Okay, and then the measure SQNR is 12.81 decibel. At 3 bits we get 8 levels, and the SQNR is 19.09 decibel. As we increasing the number of levels number of sorry number as we increasing the number of beats, the SQNR keep increasing. That we can see that beats is proportional to SQNR. Okay, um, finally at 8 bits we have 256 level, and the measured SQNR is approximately 49.79 decibel. If we compare this with the then the theoretical SQNR at 8 bits is about 49.92. Okay, so the difference is very small, only around 0.13 decibel. This showed that our simulation is behaving quite close to the theoretical result. Now, here you can see the 3-bit pulse code modulation example. For 3 bits, we have 2 to the power 3 equal to 8 levels. Now, in this output table, we can see the original samples, its quantization index, and the binary codeword and the quantized value. For example, the first sample is approximately 0. Okay, first sample is approximately 0, but after quantization, it becomes 0.1250, 0.125. In its index is 4, and the corresponding binary code word is 100. The first several samples have very similar values, so they are mapped to the same quantization level. This is a simple way to understand actually what happens during the PCM encoding. Okay, now move on to the visualization or output graphs. What we get, the first graph compares the original sine wave with the 3-bit quantized signal. We can see clearly the original signal is smooth. Okay, here you can, blue line is original, and the orange line here you can see is the 3-bit quantized signal. And while the quantized signal looks like a staircase. The staircase effect happens because we only have 8 possible levels for a 3-bit quantizer. If we more bit, the number of steps increases, and the quantized signal becomes much closer to the original one. The next graph is a SQNR versus number of bits. Okay, here both measure and theoretical curves are increasing almost together. The important observation is that the skewer improves by 6 decibel for every additional bit. The last graph shows, and here you can see MSE versus number of bits. Here the MSE decreases as we increase the number of bits. So basically, more bits means more levels, smaller step size, less quantization, and better signal quantity. So finally, we can say that this experiment successfully demonstrates uniform quantization and PCM encoding using Python. And from this result, we can clearly see that increasing the number of bits improve the quality of the quantized signal. The SQNR increased about to 12.81 decibel at 2 bits and 49.79 decibel at 8 bits. The average implement, the average improvement is approximately 6 decibel per bit, which is very close to the theoretical value of 6.02 decibel per bit. There is a small difference between the measured and theoretical result. And according to this report, this is mainly because of the way of boundary samples are how handled, and because simulation uses a finite number of samples rather than an ideal infinite standard. So that's all about my experiment number 4, which is uniform quantization and pulse code modulation. I hope this presentation gives a clear idea about how quantization works and how PCM converts samples into binary code words, and why increasing the number of bits improves the signal quality. Okay, and thank you very much for watching this video.